Okay, welcome back, everybody. Sorry about the delay. I had the meeting. I had to. We just got finished. So anyway, thank you for showing up a few minutes late. I appreciate it. Any questions before we begin? I just want to remind you the exam, which is exam number 3, chapter 7 through 9. Okay, it does open up. It should open up today. Some of you wanted it open up today and it's due on Saturday. So if it's not, I'll fix that. Okay. All right. Any questions before I continue? Feel free to either write in the chat or unmute yourself. Yeah. Well, let me continue then with chapter 10. Okay. Chapter 10. Give me 1 second, I can rearrange here. All right, chapter 10 deals with chemical reactions. We did introduce some of the chemical reactions. There's only 6 types of chemical reactions that we're going to talk about. And we did introduce one of them already with the chapter on acids and bases, where we had the neutralization reaction, the reaction of an acid and a base. Okay, so we're going to introduce 5 other ones. Now, along that, keep in mind now what we've been doing, let's kind of put everything together, at least attempt to. We started off with the atoms, okay, from the atoms and periodic table, at least for the main elements of the metals. We determine what kind of oxidation state they have, what kind of charge they will have when they lose electrons. For the non-metals, we also did the same, because they're going to gain electrons, they're going to have the new charge. And then we started putting molecules together by putting these ions together. Okay, and now we're at the state that we're going to get these compounds. We put the ions together, make compounds. Now we're going to get the compounds to react with each other to the different types of reactions. Now, one of the aspects about reactions is we have to follow the laws of the conservation of matter. Okay, that matter is neither created or destroyed. It's just basically just moved around. It just moved from one form toward the other. Meaning, for example, that if you do a reaction and you know the total mass of all of your reactants, okay, then after the reaction is done, you should end up with the same mass as products. Okay, so if I start off with 10 grams of reactants, whatever they may be, let the reaction proceed. At the end, when I add up everything as far as weights are concerned, I end up with 10 grams of material. Now, when we were doing face-to-face, I had a little experiment that I could demonstrate there in class, this actual conservation of matter. And let me see if I can draw it out. Okay, so we all seen a Erlenmeyer flask. I'm fairly sure in the lab part you've seen Erlenmeyer flask. Erlenmeyer flask looks something like that. I'm not an artist, so bear with me. Now, in there, we would put a little bit of liquid and explain what that liquid is, but it would be sitting on a balance, electronic balance. In that liquid, it would be acetic acid, aka vinegar, aka vinegar. All right, so here's the lip of the Erlenmeyer flask. Now, on that, we would attach a balloon. Okay, and in that balloon, we would put in the balloon some sodium bicarbonate. And that simply good old AKA baking soda. Okay, so we got AKA vinegar, and then we got AKA in the balloon hanging to the side sodium bicarb, which is a base. Okay, and the acetic acid obviously is an acid, so we had an acid-base reaction going on. So then we take that balloon and put it straight up, and the baking soda would then go into the acetic acid, which causes a reaction. One of the products that was created was carbon dioxide as one of the products. So you can see here, hopefully, that uh, what's going on with respect to the balloon is that balloon would capture the CO2, okay? And we got the liquid sitting in here, and we will weigh this thing out because it's on the analytical balance, and that could be, let's say, 100 grams of material that we would measure before we added the bicarbonate, open and straighten up the balloon, and then let it run for a few minutes. Reaction proceeds, it gets all bubbly up in here, balloon captures the CO2, and guess what? That balance would fluctuate very little. You'll still get 100 grams of material, and that really demonstrated the law of conservation of matter. Yeah, with time we start to lose a little bit, and that's simply because our connection here was not airtight. And so, yeah, you lose a little bit, but if we have better connections, you can see that 100 grams before, 100 grams after. The carbon dioxide, the carbon, okay, in the form of carbonate, gets converted to carbon in the form of carbon dioxide. It is still carbon, okay? Nothing's changed there. It is still carbon. It's just in a different form, okay? All right. Now, the conservation matter says that if I start off with an X number of carbons, for example, or any of the elements, and let's hear they're saying 254, at the end, I'm going to end up with 254 carbon atoms or any other elements that's involved in the reaction, okay? They're just going to be in different forms. And what we do is we start adding coefficients to balance these chemical reactions, okay? And so we could have generically, let me just write a generic question here, equation. So we got A plus B reacting to give us maybe, maybe AB compound. And for whatever reason, we need two Bs, okay, to react with a single A. So these coefficients right here, and it's understood when there's no coefficient in front, it's understood to be one molecule of A. There's two B, and there's one of AB subscript 2, okay? And so we have a balanced chemical equation. These coefficients we're going to use down the road when we start calculating, doing some calculations, chemical reaction calculations. So we could, for example, say, if I start off with 10 grams of A, can we calculate how many grams of A subscript 2 we will make? And yes, we can, okay? But it's important that the coefficients are correct so we can do an accurate calculation. All right, so that generic equation is a balanced chemical equation. So we add coefficients as necessary. So the number of atoms as reactants equal the number of atoms as products. Now, in these 6 reactions we're going to talk about, some of these different types of reactions, when it comes to the balancing part, unfortunately, is a trial and error. You put a coefficient, you observe, I need 2 of these on my reactant side, so then I put a 2 there, which then pushes up maybe another element, so I go over to the product side and maybe add another number, and I go back and forth until I got the number balanced. And it's a trial and error, unfortunately. However, some of these other reactions, we have a systematic approach that we can tell you this is how you're going to balance this type of chemical reaction, okay? So in balancing chemical reactions, first you're always going to write the chemical reaction, making sure the chemical formulas are correct. And that the ionic formulas add up to 0 charges. It's no different than what we've been doing, okay? We've been putting together, either we take the name of the compound, either a covalent compound, and from the name we write the formula, or the ionic compounds, we take the name of the ionic compounds and we write the formulas. Now, with respect to the ionic compounds, we first write them out as ions. They're, so that when we put them together in the right ratio. And then we that gives us the formula, okay? So it's a continuation of what we've been doing so far. Then once you put that reactants together and the products, and then you start playing with the coefficients and writing a coefficient such that the reaction is balanced and that we have the same number of elements in the reactant side equal the number of elements in the product side, okay? So, for example, we have a simple equation, okay, which is the combustion of hydrogen gas in the presence of oxygen yields water. And you could be given this reaction in just those words. Hydrogen in the presence of oxygen reacts to give you water. So you take that wording and you convert that to the chemical reaction. So plus, we're going to have to refresh your memory on such things as a physical state. So if we recall, we talked about this, which elements are salts, which are liquids, and which are gases, okay? Also, we looked at the solubility rules and determined from the solubility rules whether the compound that we make is soluble in a solution or not. All right, so here we have hydrogen in the presence of oxygen yields water. Specifically, 2 molecules of hydrogen. Notice that 2 molecules of hydrogen and 1 molecule of oxygen reacts to yield 2 molecules of water. Okay. Note the hydrogens. The hydrogens are in the grayscale. There's 4 on the left-hand side, and there are 4 in the right-hand side. The 4 on the left-hand side are the hydrogen in elemental form. There's 2 molecules in it. Okay, let's take a look at the oxygen. There are 2 oxygen atoms on the reactant side, and there are 2 oxygen atoms on the product side in the form of water. It is still oxygen. They are still hydrogen. They're just simply in different forms. And so we put that coefficient here to tell us there are 2 hydrogens, okay? So it means we got 4 hydrogens total, okay? And then we got 2 oxygens on the reactant side. And then we go to the product side, and you can see we got 4 hydrogens total on the product side and 2 oxygens on the product side. We are balanced, okay? Regardless of what form they're in, it's oxygen is oxygen in the form of oxygen, a molecule of oxygen gas, or in the form of water, still oxygen. Now, the other aspect about balancing the chemical equation with its coefficients is the ratio between hydrogen and oxygen is a 2-to-1, which means this will bring you back memories now when we were doing the conversion factors. Remember that chapter, conversion factors? We had a conversion factor 1 inch is equal to 2.54 centimeters, and we were able to write a ratio with either centimeters in the numerator or in the denominator. We can apply that technique here also. So we can write a ratio of 2H2 over 1 oxygen. Okay, or I can just simply invert it and write it the other means. And that is the relationship between the 2 reactants. Okay, now as we did back then with the conversion factors, it depends on which one we use, the left or the right, depends on the question we're asked and depends on the units. Okay, and so for example, if the question was, if I have 100 hydrogen gas molecules, how many oxygens do I need? Okay, so if I have 100 H2Os, how many oxygens I need? Okay, well, we write down like we did before with the problems. Remember the conversion factor, write down what we have what we are given, we got 100 H2Os, okay? I'm going to need a factor here. And obviously I need hydrogen in the denominator and oxygen in the numerator, because why? That is what we're looking for unit-wise, O2, okay? And then I take this ratio, I get it from the balanced chemical reaction, and I'm going to use the one on the left, where I got the ratio of 1 to 2, okay? And so you can see how hydrogens cancel out. It's telling me that if I start off with 100 hydrogen molecules of 100 molecules of hydrogen gas, I need only 50 molecules of oxygen gas, okay? And right now I'm saying just molecules, but we're going to be using the factor called mole, and it's a very important concept in chemistry, because with the concept of the mole, M-O-L-E, kind of introduced it a little bit when we're talking about pH. But the mole is our conversion factor from going from A to B, from going to hydrogen to oxygen. I can't go directly unless I go through the units of mole, and that's the common factor. Analogous to fruit, apple, bananas. I can't go to an apple to a banana correlationship, but what they have in common is the unit of fruit. If I have a conversion factor, boom, I can convert, okay? And now, that's the ratio between the two reactants, but you also have a relationship between the reactant oxygen and water, which is a 1 to 2, okay? And you have the relationship between hydrogen and the product, which is a 2 to 2, okay? So in essence, you have a total of 6 ratios here that relate either the two reactants with each other, or one of the reactants with the product, and then the other reactant with the product. And these ratios is what we're going to need when we start doing the chemical calculations. But if you don't balance it correctly, then you can see here quickly that if this was inadvertently a 1 instead of a 2, then you would calculate you need 100 molecules of oxygen, which would be incorrect, okay? So balancing the chemical reactions are a crucial part, crucial step in the calculations of chemical reactions. All right, so let's take a look at this one here. We have, and it could be written out, written in the form of as follows. It could be written like nitrogen in the presence of hydrogen reacts to give ammonia, okay? So with that verbiage, that wording, then you take that wording and convert it to a chemical reaction. Right, so we have nitrogen gas reacting with hydrogen to give us ammonia, NH3. Yeah, be familiar. You're going to use this. You're going to see this NH3 quite a bit. So if you don't know it as ammonia, I would stick it in long-term memory. You'll see it numerous times. All right, so let's figure out where we're at with respect to balancing. That's the chemical reaction, but are things balanced? Well, what I do is I generate a grocery list of atoms, okay? So on the left side, I got 2 nitrogens, right? And I have 2 hydrogens, okay? Product side, I got 1 nitrogen and 3 hydrogens. So right away, you can see that nobody's balanced here, okay? I got 2 nitrogens on the left, 1 on the right. Now, these equations that we're going to work with are small enough that you can do a trial and error, okay? You can go that route, but you can pick up on some little tidbits. For example, remember when we were doing a combination of, let's say, dissimilar charges, we were doing, I'm trying to think of one real quick. Here I am trying to think of one, and I'm having a senior moment here. Oh yeah. Okay, remember we were trying, let's say, to combine magnesium, which is a +2, and maybe nitrite, okay? And what do? We look for a common number. Remember that? Our common number here was 6. So I needed 3 magnesiums and 2 nitrites. So the formula was Mg3 and 2, okay? So very similar and very analogous here too, because I got on the left side, I got, when I just look at the hydrogens, I got 2 on the left, 3 on the right. So what if I look for a common number, right? Which is 6 again. So that means that I would need 3 hydrogens on the left side. All right. Oh, this is hydrogen. So that, and then 2 on the right side. Okay. So that means that my 2 now is now 6 hydrogens. And on the right side, now I got 6 hydrogens. Okay. And adding the 2 here, that kicked up my nitrogen to 2. And by default, that balanced out the nitrogen on the reactant side. So it definitely looks like we have a balanced chemical reaction here. 1 molecule of nitrogen gas requires 3 molecules of hydrogen gas to yield 2 molecules of ammonia. Okay, here's 2. All right, so we are balanced there. And another way to look at it is just simply see, let's break it down. You got nitrogen there, and then you got 3 molecules of hydrogen. Oh, that's hydrogen. And then yields 2 ammonias. Okay. So you can see the 6 hydrogens, and then the 6 hydrogens here in the form of ammonia, the 2 nitrogens, and the 2 nitrogens. So we have balanced chemical reaction. Notice the ratio, always be aware of the ratio. It's a 1 to 3 between nitrogen and hydrogen. It's a 1 to 2 between nitrogen and ammonia. It's a 3 to 2 between hydrogen gas and ammonia. Okay. All right, now we have this one here. We have hydrogen in the presence of bromine, okay, reacts to give hydrogen bromide. Okay. Notice there's something here. This being a gas, this is for nomenclature, hydrogen bromide, bromine. But the moment it becomes an aqueous solution, it's called hydrobromic. I said bromine, it's bromide, excuse me. Okay, hydrobromic acid when it's in the aqueous phase. So be aware of that when you look at the nomenclature exam, which, by the way, I haven't converted those numbers to 0. You haven't done an attempt, so we'll be doing that this weekend. Give you a heads up. So we're halfway through the semester, and you have unlimited attempts for that nomenclature exam, but you must score at least an 80 to pass that quiz. Okay, so you can take it as many times as you want. Once you hit that 80, if you want to continue to improve on it, you can continue. You don't have to stop at 80. So, but it does have an effect on your grade. So right now your grade is without that, and it's like once I put a 0 in there, it can give you a better feel for what your grade truly is. And I don't, as I explained earlier in the semester, I used to wait till the end of the semester, but then, if I did do that, then you realize, oh, I'm doing good, but then if I put the 0 in there, the grade drops drastically, and now you got a week or 2 to try to get that thing in there. So do it early in the semester, so you have plenty of time to get that 10% in there for you. All right, the next one we have HBr. So how to balance this? Well, we got 2 hydrogens on the left, 2 bromines on the right, and so you know what if I just simply put a 2 in front of HBr? Good enough, it does. I have a balanced chemical reaction here. Okay, just by simply putting a 2 in there. Okay, so this is what I mean by trial and error. You kind of look at the problem, look at the reactants, both reactant and the product side, and play with the numbers so that you can get everything to balance out for you. Okay, and these type of reactions are small enough so that you don't, they're not like they're not that complicated with respect to being able to balance, because they can be. If you try balancing complicated reactions and you try balancing by trial and errors, it's a tough thing. All right, the next one you have to be written as carbon monoxide in the presence of oxygen, use carbon dioxide. And this is one method to get rid of carbon monoxide, is to react it with more oxygen, and you end up with carbon dioxide, which is not a poisonous gas. Okay, so what we got here is a couple of things here. There's no right way or wrong way, whatever works best for you when you do the trial and error method. But a suggestion would be, we got one carbon on the left, one on the right. Carbon seems to be happy. Okay, but we have three, an odd number, 3 oxygens. You got one carbon on both sides, 3 oxygens on the left side, and then we got 2 oxygens on the right side. Okay. Maybe if we put a 2 in front of carbon monoxide, what does that do? Well, that kicks up my carbons 2, and my oxygens now goes from an odd 3 to 4, which is something good to work with if you can use even numbers. Not always the case, but pushing everything to even numbers would help. And so now, if I put a 2 in front of carbon dioxide here, that kicks up my carbons, right? At the same time, that also kicks up my oxygens to 4. And so does it look like we're balanced here? Sure does, doesn't it? We got 4 carbons on the left, 4 oxygens on the left, 2 carbons on the left, 4 oxygens on the left, and then 2 carbons on the right and 4 oxygens on the right. So that definitely did work. And we are balanced. So we need 2 molecules of carbon monoxide for every 1 molecule of oxygen. Okay. All right, so in writing reactions from words, like I've been converting the examples we just did, remember about the physical states, okay, of these species, whether something's a solid. Now, if it's a solid, it's probably because it's if it's an element, there's majority of the elements are solids. There's only 2 liquid elements, and then there's like a dozen gas, right? So in the elemental form, remember that. Also, if it's an aqueous solution, based on the solubility rules, that material could be a solid. So the solid applies to if it's an element that's a solid, or an ionic compound, because the solubility, it is a solid. Okay. And if it's an ionic compound that, based on the solubility rules, that it is soluble, and then we use the AQ. Okay. Solid, liquid, and gases, I just mentioned that. And of course, don't forget the elements that are diatomics. There's only 7. Have no fear of ice cold beverage. Okay. Because the example we did earlier, we said hydrogen in the presence of oxygen. Well, if you take that and you simply write H plus O gives me water, well, right off the bat, that just won't work, okay? Because hydrogen, you should know, that is diatomic. There's only 7 of them. So that is the incorrect formula for hydrogen. And I've seen this a lot where I got hydrogen by itself and oxygen, and people just put a 2 there and it's balanced. Yes, it's balanced, but it's not correct with respect to the formula for the reactants. So we know that oxygen and hydrogen are that common. And that's true for all the other ones, okay? We know that subscript tells how many elements are in that compound. So the subscript 2 here represents 2 hydrogens for every oxygen in the molecule of water, right? The coefficient tells us how many of those molecules we have. Okay? Coefficient. Now we can change the coefficient as many times as we need. The subscript, that's etched in stone. Once you determine what the subscript is, that doesn't get changed. Okay. All right, so we have this reaction here. Written out in words, they're telling you sodium reacts with chlorine to produce solid sodium chloride. Okay, so let's break down what we're given. Sodium. Now the word sodium, it's just the name sodium all by itself. They're not talking about sodium and chloride, not at this point, it's just sodium. So we have sodium, which tells us it is the element sodium. And remember that table, the periodic table that we have given to you. It's on one, the chapters that showed which elements are solids. And you'll see there that sodium is a solid. Reacts with chlorine. Okay, chlorine, the I-N-E tells you we're talking about the element chlorine. And chlorine is one of the diatomic species. Furthermore, it is also a gas. Okay. To produce, okay, some keywords. Sodium reacts with is a keyword for plus. Okay. To produce is a keyword for the reaction arrow. Or it could be words like yields or gives or makes, words like that. Tell you that's the arrow. And then the followed by whatever chemical follows that to produce is the product. Here we have sodium chloride. So sodium chloride tells you it's an ionic compound, plus you're giving you the physical state. So we need to first write the ions first, which sodium is a +1 because it's a group 1 element, okay, 1A element, got 1 valence electron, it's a metal, it's going to lose that electron, so it has a +1 charge. And chloride, the keyword suffix is IDE, tells you this. It's not chlorine, the element, but chlorine, the ion. And that's group 7, it's a nonmetal, and so it will have a -1 charge because it gained 1 electron. So now I can put them together, 1-to-1, because the respective charges cancel each other out, so I just need 1 of each. And there's the physical state, which is given to you in the word problem. All right, now we have the base chemical reaction. So the next step is balancing it. And this is pretty straightforward. We got 2 chlorines on the left, 1 on the right. So I just simply need to put a 2 in front of sodium chloride, which balances the Cls. Okay, but it ups my sodium, so no problem. Come to the reactant side and put a 2 in front of sodium. Now I have a balanced chemical reaction. And this reaction is a 2-to-1 ratio between the sodium and the chlorine. Okay, so it takes two atoms of sodium to react with 1 molecule of chlorine to give us 2 molecules of sodium chloride, aka table salt. Okay, so very hazardous metal, very poisonous gas, results in giving us a material that we can safely put on our French fries. And all what happened was it lost an electron. Now, watch carefully here, okay, because it's all related. Sodium here has a oxidation state of 0. Does it not? The element sodium has no charge, okay, because it has an equal number of protons and electrons, okay? And the same is true for the chlorides. They have no charge, zero charge. But then what happens to the sodium? It becomes a +1. So it went from a 0 to a +1 oxidation, okay? +1 to oxidation state. So that is a specific type of process that we're going to talk about here in a second. Same token, the other direction is that the chloride gained an electron. It went from a 0 to a negative state, and by gaining an electron. And that process has a specific name. All right, so let us continue with this one. So there's the basic formula as we wrote it, okay? Then we added the states, okay, physical states, and then we balanced it out, okay? Now, obviously, you might, and I've seen this before, because it's assumed it's a Cl2 here, that is the formula for sodium chloride. Now, it doesn't make sense for that to be the sodium for sodium chloride. And why is that? As I stated earlier, sodium is a group 1 element. It only has one valence electron. This infers in this formula that sodium has a +2 charge because each chloride has a -1, right? And it can't have a +2 charge because it only has one valence electron. And to lose a second electron means to pull it off the next shell in, which is full, which is not energetically favorable. So that formula just would not be totally incorrect with this, with NaCl2. Okay. All right. Here's another reaction. We're going to convert that from words to a chemical reaction. So we have the first one, which is aluminum. Okay, that's Al. It's a metal. It's also solid. Reacts with, that's our key word for plus. And then we have bromine, just like chlorine. This is the diatomic element. Okay. And anybody know what bromine, what physical state bromine is? Is it a solid, liquid, or gas? Okay, we'll come back to that. Think about that. Bromine, to produce is our key word for the reaction arrow. Okay, solid aluminum bromide. All right, so we're going to write the product. It's ionic compounds, so we're going to write them as ions first. Aluminum is a group 3 element. It's a metal. It would lose those 3 valence electrons. Bromide start as a group 7, so it gained 1 electron. It's a nonmetal. So that means we need 3 bromides for every aluminum ion. All right, so our formula becomes AlBr3. Okay. All right. Bromine, that's good, Debbie. You're correct. Bromine is a liquid. One of only 2 liquids of the elements. The other liquid is a metal, and I'll let you guys figure which one that is. All right, so then it's a solid, so you're told what the material, the physical state of the product. All right, so here we go. We got the basic chemical reaction, but it's not balanced, obviously, right? Because we got 1 aluminum on the left. We got 2 bromides. I'm just calling BR because it's either going to be bromine or bromide, so I just say BR. 2 BRs on the left. We got 1 aluminum on the right, and we got 3 BRs on the right. And when I mean right, I'm talking product. Okay. to the right of the arrow. So obviously the BRs are not balanced. The aluminums are good, but the BRs are not. Second of all, we have a dissimilar number here. We got a 2 and 3 scenario, okay? And so mercury, you are correct, Debbie. Mercury is the other liquid. And so we got a 2 to 3 relationship here that we've applied for other things. We can do it here too. So if I find a common number, if I put a 3 there, that gives me 6 BRs on the reactant side. And if I put a 2 here, that gives me 6 BRs on the product side. So the BRs are balanced. That also kicks up my aluminum to 2, so no problem. Now I go over to the reactant side, put a 2 in front of little L there, and now I'm balanced. So I put these things down here at the bottom to help me keep track of where I was and where I'm going with respect to balancing them. Once I'm done, I'm done with it. So I got a balanced chemical reaction here. Notice the ratio between aluminum and bromine. It's a 2 to 3. Okay. And then from bromine to aluminum bromide it's a 3 to 2. And from aluminum to the product, it's a 2 to 2 or a 1 to 1 relationship. Okay. Here, let me clear up my mess and just put something down that's not so messy. So there's the formula we just wrote. Okay. Then we added the physical states, and then we came back and balanced it at the end. So we got a 2 there, got a 3 there. Find that common number. We got a 2 there, balancing aluminum. And so now we have a balanced chemical reaction with the proper, correct formulas. And don't forget the ratios. Look at the ratios between reactants. I can write it with 2 aluminum in the numerator or 2 aluminum in the denominator. Which one I need to use, totally dependent on the question being asked, okay? These reaction ratios. All right, here's one that's nothing to do with ionic compounds. So what we're doing here is basically writing the reactions for covalent compound. Okay, so we have write the reaction of phosphorus reacting with oxygen to make solid diphosphorus pentoxide. All right, so we got phosphorus, so phosphorus is a P, and we know that that's a solid. Okay, reacting with is our key word for plus. Okay. Oxygen is diatomic. Okay, it's O2 and it's a gas. Okay, to make, that's our key word for the reaction arrow. And now we have solid diphosphorus pentoxide. Remember these in nomenclature chapter? We're given a name. Now write the formula. Write down the base formula first. We got phosphorus and oxygen, and then come back and do the prefixes. Pent is 5, and di is 2 phosphorus. So we have P2O5, excuse me, plus it's a solid. Okay, so we've written down the general formula, and obviously it's not balanced, right? Because we got 2 oxygens on reactant side, 1 phosphorus. We got 2 phosphorus on the product side and 5 oxygens on the product side. Now, like we had before with the 2 to 3 disparity, guess what? We can still do that technique, and just the disparity is different. Instead of a 2 to 3 ratio difference, we got a 2 and 5. Look at the oxygen. So the common number here is 10. So I can put a 5 in front of O2, that gives me a total of 10 oxygens, and then put a 2 in front of the P2O5, and that gives me 10 oxygens, but then that kicks up my phosphorus to 4. All right, no big deal. We can add a 4 in front of phosphorus and we're good. So it's a general guideline. If you have a reaction with an element all by itself, an elemental form, try to leave that toward the end. Save that for last as far as trying to balance it first, because eventually you can see at the end, we just need a 4 phosphorus. I just simply put a 4 in front of P and we're good to go. And so now we have 4 phosphorus, 10 oxygens on the left side, 4 on the phosphorus on the right, 10 oxygens on the right. We're good to go. It is balanced. Okay. And there's the physical states, which we did, and there you go. And furthermore, look at the ratio. So we got one ratio of 4 phosphorus to 5 oxygens. Okay. Or we can just invert it. Okay. And that's between the reactants, but we got one between the phosphorus, which is 4P over 2 P2O5s. Okay. Or you can write that inverted P2O5 on the numerator, 4P. Now, obviously, you know that 4 over 2, it's the same thing as, 2 over 1, but I recommend just leave the coefficients there so nothing gets lost down the road. And then we have the relationship between O2 and the product. So we have 5O2 over 2 PTO5s. Okay, is one or inverted. So 2 PTO5s over 5O2s. Okay, so we got a total of 6 ratios that we can utilize for this simple reaction. And fortunately, it's balanced correctly. So we can go from any direction, from phosphorus to product, from oxygen to product, or even from product to reactant. Because even in the quote, real world, as they say, this reaction that is here is that ratio pertains to whether you do it in the lab with milligram samples, or you have an industrial plant where you're dealing with tons of the material. You might be asked, as the chemical engineer, I need to make 10 tons of this material, okay? And with that information, you need to figure out, well, how much oxygen do I need? And how much phosphorus do I need? All right, and the chem engineer can calculate that real quick. And that's the difference between a chem engineer and a chemist. Yes, we know the chemistry, both of us, but the engineer is more involved of moving big tons of material from point A to point B. Because if you're in the lab, it's not a big deal. 5 milligrams, you can carry that, no problem. But 5 tons, a totally different story. All right, so you need some engineering there. All right, now this one, it says do it home, but we're gonna break it down and do it here. Okay. Now up to this point, let me break it down. Let me back up. All these samples we just did, if you look at them carefully, you'll see a general similarity, like the aluminum and bromide. Well, what's happening here, you have 2 elements that are put together to form a compound, okay? You got this element forms a compound. See that? Next one. We did this one, okay? You got this element forms a compound, okay? In fact, this is a type of reaction, one of the 6 I'm going to talk about, and this is called a combination reaction. All this will be summarized here in a few slides. Combination, if you think about it, makes sense. I'm combining 2 elements phosphorus and oxygen to form a compound. Okay. And if you go the opposite direction, if I start with a compound and I break down that back to the elements, that's called a decomposition reaction. So you decompose it. So if you take a compound and you break it down to the elements, you decompose it. That's the opposite of a combination reaction. Okay. So just FYI, so you'll see it here in a bit when we start talking about these reactions. Right now, we've been practicing figuring out how to balance these reactions. Okay. Now, for these type of reactions, like we've been doing, these types right now are basically a trial and error. We see a number, we look at how many elements we need on the left and right. We start plugging numbers in and see how that works for us. Now, once you balance a reaction and you come up with, let's say you come up with double these numbers. Let's say you come up with 8, 10, and 4. Okay. Yes, those are balanced. That's a balanced chemical reaction. But by convention, what you want to do, once you put the coefficient in there, reduce them down to the lowest terms. You give you a whole number, not fractions, but a whole number. So that 8, 10, and 4 are all divisible by 2. Okay. So they can, 1 second. All right, they're all divisible by 2. So you want to produce those as produce your numbers as whole numbers, okay? In the lowest terms. That's right. All right, so this brings us to another type of reaction. Now, here, these are called a double displacement reaction, but we're not going to worry about the name right now. What we're going to do, we're going to break this down. It looks very complicated. Think about it. Read it. It says, right, then balance this aqueous reaction. We have nickel 3 sulfate plus lead 2 nitrate produces nickel 3 nitrate and solid lead 2 sulfate. Okay. All right. So looks complicated, but I'm a big advocate in you take complicated things, you break it down stepwise. All right. So let's break it down. Let's first write these compounds and let's put them together to write the formula. So that means that we're going to, let's look at the first one, nickel sulfate. Okay. So Roman numeral 3, remember what that means? That is the oxidation state of nickel. So we're using nickel plus 3. Okay. Sulfate, that is the polyatomic ion, and that is SO4 negative 2. Okay. So we'll put them together in formula here in a bit, but first let's write them in ion form. Plus, that's the other reactant. We got lead 2. Lead Roman number 2 is we're using lead plus 2. Okay. Then we got the nitrate, and that is the NO3 minus 1 species. Okay, directed to the polyatomic ion table for both the nitrate and the sulfate. Produces is our key word for the reaction arrow. Okay. Now, when you see these type of reactions, 9 times out of 10, the oxidation state of the metals will remain the same. It is feasible to start off with nickel 2, 3, and then get converted to another oxidation state, but we're going to always keep them the same. Produces nickel 3 nitrate. So we got nickel 3 again, plus 3 nitrate, okay, which is the NO3 negative, and is a key word for plus, solid, they're telling us the physical state, of lead 2 sulfate. So Pb plus 2 and sulfate, SO4, -2. And it's going to be a solid. Write that down so I know, keep track of that. So those are the ions, okay? So now I'm going to put the species of the ions together in the correct ratio. So we got a dissimilar charge here, a +3 and a -2, like we've been doing before. Find a common number. That means I need 2 nickels and I need 3 sulfates, okay? So its formula is Ni subscript 2 SO4 subscript 3. So that is the formula for nickel 3 sulfate. Plus, we got lead +2, and the nitrates are -1. So that tells me I need 2 nitrates for every lead +2. Okay. So its formula is Pb, parentheses, because this is a polyatomic ion, and we keep it together as a unit like the sulfate, and I use the parentheses subscript 2. So that is the formula for lead 2 nitrate. Now let's put together the products. We got nickel nitrate, which means I need 3 nitrates for every nickel +3. All right, so it goes Ni parentheses NO3 subscript 3. Okay. And then plus lead 2 and sulfate -2. They're both the same charge. I put them together as a 1-to-1. So it's Pb SO4 plus the physical state is solid. All right. Now, in the beginning, they said the aqueous reaction. So nickel sulfate and lead sulfate are soluble. In fact, if you look at the solubility rules, you'll see that this particular sulfate with the nickel is soluble. And the lead nitrates, no matter who the nitrate is bonded to, okay, it's soluble, which is the same thing here for the product where you got nickel nitrate. It is soluble in water, so it's AQ. Okay, so look at what happened. The respective ions simply exchange partners. The nickel recombined with the nitrate, okay, to form the nickel nitrate, okay. The lead recombined with the sulfate to form lead sulfate. So in essence, the two reactants, which are soluble in aqueous systems, and if you put them in little test tubes, they're both clear solutions, okay? And then what happens is when you mix them together, they just change partners, and because of the solubility of one of the partners, specifically the lead sulfate, you form a cloudy solution, you precipitate, okay? And this is a type of a reaction called a double displacement reaction. And it's only positive because the two new products that are generated, one of them was insoluble. If both of the new products were both soluble in the aqueous system, then you have a negative reaction, okay? So this type of reaction is governed by the solubility rules of the products. All right, so we wrote the equation as given to us in the wording. Now we got to balance it, okay? Now, balancing these types of reactions, you might look at it on the surface and say, oh my goodness, there's so much here to keep track of. But keep in mind, the parentheses are the polyatomic ion tables. Don't try to count every nitrogen and every oxygen. Trust me. Count the units of the polyatomic ions, and keep track of those. Follow the polyatomic ions. Once you do that, the metals that are attached to it just fall into place and get balanced by default. Okay, and so let's look at the polyatomic ions. Okay, and let's just focus on one of them. Okay, let's focus on the nitrates. So we got 2 nitrates on the left and 3 nitrates on the right. Don't we have a dissimilar situation here again? Sure, no problem. So what I do is, like we've been doing before, if I put a 3 in front of the lead nitrate, then now gives me 6 nitrates, right? And if I put a 2 in front of nickel nitrate, now I got 6 nitrates on the product side. Okay. So the nitrates are taken care of. Now focus on the metals for those nitrates. The lead got kicked up to 3 because we added a 3 in front of lead nitrate. Okay, no problem. Go to the product side and put a 3 in front of lead sulfate. That balances out the lead. The nickel on the product side is 2. Okay. By default, the nature of the beast, the nickels are taken care of because we start off with nickel subscript 2. So nickels are good. Okay. And let's find out if everybody's good. We got 2 nickels on the left. They check out. Nickels are good. 2 on the right. We got 3 sulfates on the left. And guess what? We got 3 on the right in the form of lead sulfate. So the sulfates are good. We got 3 leads on the left, 3 leads on the right. We got 6 nitrates on the left, 6 on the right. So everybody's happy and we got it balanced. So we took this look at like sophisticated looking equation, looking difficult, broke it down to the ions, put them together with the right formulas, the right ratios, and then to balance them, follow the polyatomic ions. Okay, so there is a little bit of technique with respect to these types of reactions, and again, this is called a double displacement. DIS placement reaction, RXN, shorthand for reaction. And they are governed, this type of reaction is governed by the solubility rules of the products. If one or both products are insoluble, then you got a positive reaction. If both products are soluble, then you got a negative reaction. Okay. And so already we've touched on acid-base reactions, right? I just talked to you, introduced you to combination reaction, then a decomposition reaction, which was the opposite of combination reaction. And now we got this one here, which is called the double displacement reaction. That's 4. And then the 5th reaction, which you're already familiar with, is called the combustion reaction. Anytime you burn something, that's a combustion reaction. Okay, we'll give you more details on that in a bit. And then that just leaves us with one type of reaction to work with, to tell you about. All right, let me clear up my mess here and bring it out. So there's the reaction. Oh, there's the reaction, all balanced and ready to go. Okay. All right. So in general terms, the 6 types of reactions are as follows. The first one is called a combination reaction, where you have 2 different elements. Okay. 2 different elements. And that's how you recognize that you have a combination reaction, is the reactants are elements. And then when they combine, they come together, they form a compound. In this case, the compound in generic form, in generic letters, are AB. Okay. And a good classic example of that one is I won't balance it, but it's hydrogen in the presence of oxygen reacts to give you water. Okay, hydrogen the element, oxygen the element, combine to form the compound water. Okay. The opposite direction is when you take a compound and you do something to it and you break it up into their elements. And another, the classic example here is, again, you can take water, H2O, and undergo electrolysis and break it back into the elements of hydrogen and oxygen. Okay, that's why water is very important to find out in space, because we can undergo hydrolysis to generate oxygen for us to breathe. And hydrogen is about the good fuel to use. Fuel. All right. Combustion reaction. Here's the one I was just talking. Combustion reaction is this. For us here at Chem 130, we are talking about the combustion of only what are called hydrocarbons. Okay. And here we got a subscript X and subscript Y. X, the smallest number of X is 1. So the smallest hydrocarbon, and H, the smallest number, H is 4. This is methane gas. Hydrocarbons made up of nothing but carbon and hydrogen. That's it. Okay. And so, as any combustion reaction for anything to burn, you need oxygen. So you should know that that's a reactant. Okay. Because you could be given the problem here. What's a combustion? Write the equation for the combustion of methane, and they give you CH4. Well, you should know that you're going to need oxygen, because without oxygen, it's not going to burn. Okay. Propane, or if you got a propane grill or a butane lighter, none of those light up. None of those will burn if you don't have oxygen. Okay. Now, for Chem 130, there's only 2 products that you will get in the combustion of hydrocarbon: carbon dioxide and water. That's it. Fully understand your vehicle is loaded with hydrocarbons. Yes, your vehicle burns hydrocarbons. Also, your vehicle produces carbon monoxide. And that is because our engines are not that very efficient. Our system of combustion is not very efficient at all. And so there's a lot of hydrocarbon that do not get converted completely to carbon dioxide. Okay. There's systems in there to try to get as much as possible of that exhaust to be converted to carbon dioxide, but there's carbon dioxide still not worked out. All right, so I fully understand. But for us, Chem 130, the only 2 products you get is carbon dioxide and water. Also, we have a systematic approach on how to balance these type of combustion reactions. Okay, which you're going to talk in detail, but I'm going to give it to you now. Step number 1, you balance the carbons first. Okay. Step number 2, you balance the hydrogens next. And then finally, you balance the oxygen. Doing that systematic approach, you will get 100% of the time a balanced chemical reaction when it comes to balancing the hydrocarbons. Okay, something else. All right, let me clear this up. Okay, we talked about this reaction. It's the acid-base reaction, aka neutralization reaction, where you have a covalent compound that produces a proton and therefore defined as an acid, reacting with an ionic compound, which in solution produces the hydroxide. Okay. And when you have, and it's designated as the base, so when you have an acid in the base, The product you get always 100% of the time is water. And then the corresponding salt, which is attributed to the metal of the ionic compound, combining with the non-metal of the acid, okay? All right. We talked about the acid-base reaction. That's the fourth one. This is called a single replacement reaction. And this comes, I think, a little bit clearer when I give you specific examples. But let's look at the general equation here. We have two metals, okay? The first metal, written as M, is the element metal, whichever it may be, okay? The second metal is in the form of a ionic compound, okay? Because the ionic compound is a combination of a metal and a non-metal, okay? Now, if this reaction proceeds, what in effect is happening is the metal in elemental form gets converted to ionic form, okay, and combines with the non-metal. And so now where you had M by itself, now you have MX. Now the metal that was in the ionic form gets converted back into elemental form. A good example of this is plating. I'm sure you've heard of plating. You got a plate, like chrome plating. You got a bumper. You got to put some plating on it, some shiny stuff. Gold plating, copper plating. You can plate all kinds of metals. But basically, what's happening there in plating is you have the metal you want plated is in ionic form, and then it gets converted back to elemental form and it gets attached to wherever you're going to attach it. Okay. What governs here with this reaction is what governs this reaction to occur is what is called the activity series. Now, in your periodic table, right above the solubility rules, and we're going to talk about this at length, you have what's called the activity series. It is the listing of the relative reactivity of metals. You can see that lithium is listed first as the most reactive metal. And then it goes down the road to the last metal, which is Au, which is gold, which is the least reactive metal, okay? And depending on the position of the two metals in the reactivity series, will determine whether this reaction will proceed as written, because it's all dependent on the most reactive metal. If the most reactive metal, all metals want to be in a more stable state, okay? And in order to do that, all metals want to lose electrons. And when they do that, they become ionic. And so what's happening here, the way it's written, this shows that metal M, whatever metal that is a lot more stable in ionic form, okay? And then metal A. And that is why this reaction is written. If the most reactive metal between A and B, if the most reactive metal is not in ionic form, then reaction proceeds as written. What this tells me here is that the metal M, as far as reactivity, is a lot more reactive than A, okay? And being a lot more reactive than A, it wants to go into ionic form, and therefore will displace the A in ionic form and shove that back into element form, so it itself will be in a lot more stable state. Okay, and then finally, this is the one that we just finished doing, which you call the double replacement, double displacement, but go with replacement. Depends what book you read. So what's happening here, as I demonstrated, we have the subscripts here. Don't tell us how many atoms. They should be more of a superscript. Just tell us that M1 is a different metal than M2, okay? And so we have two ionic compounds. Okay, both of them soluble. Okay. And so what's happening, M2 then partners up with the new partner X, and then M1 partners up with Y, gets a new combination. And depending on who is soluble here or insoluble, if this one is insoluble, then we have a positive reaction. And so the solubility rules govern this type of reaction, okay? Whether a reaction proceeds or not. And if both products, both new products are both soluble, no reaction. If one or more, most of the time it's only going to be one of them that is insoluble, then you have a positive reaction. All right, so those are the 6 types of reactions that we're going to talk about. I tell you what, let's do this. I got 3:03. Let's take a quick 15-minute break. Let's come back at say 3:15. Okay, and we'll continue. Okay, we'll continue with this. So let's take a short break and we'll come back at 3:15. Okay, I'm back. Let me put the screen back up there. All right, so as we were talking about, you have the 6 different types of reactions that we're going to be working with. Okay, and for the first 2 types, as far as balancing those type of reactions, the first 2 types mostly is a trial and error, and they're going to be small enough reactions that a trial and error is probably the best technique to balance those. The combustion reactions, we have an approach on that, and that is balancing the carbon first, the hydrogen first, and then the oxygen. For the acid-base reactions, to balance that, what we do is we follow the proton and we follow the hydroxides. Okay, we have some more specific examples there in a second. Single replacement reaction, that's going to be like the combination and decomposition, more of a trial and error. And then for the double replacement, here we follow the majority of the time. You're going to be dealing with polyatomic ions. You follow the polyatomic ions to get those balanced out, like that example we just did earlier. Okay. All right, so here we have a combination reaction. Note how you recognize that. You have phosphorus and oxygen coming together, okay, to form diphosphorus tetraoxide. Okay, and so to balance these, what we're going to do is, okay, trial and error. We can we got a single phosphorus by itself. Let's leave him alone for the time being. Save him for last, a single element that's just sitting there. And let's look at the oxygen. I got 4 oxygens over here, 2 over here, no problem. If I simply put a 2 in front of O2, it balances out my oxygen, so they're good to go. Okay, subscript 2 for phosphorus. Okay, now we can put a 2 in front of phosphorus and we got a balanced chemical reaction. All right. All right, here's this one. Anybody want to take a shot at what is the name of this species right here? Fe2O3. Now, keep in mind, here the reactions are given to you and you're asked to balance it. But these reactions could be written out in words and then you're asked to write the equation and then balance them. So what would be the name of that species, Fe2O3? Anybody want to give a shot? Okay, well, let's give it the base name. Okay, so we know it's iron and it's oxide. Okay. Iron is not one of the exact, and we got the iron trioxide. Oh, no. Oh, no, no prefixes. No prefixes for ionic compounds. Okay. Only prefixes for covalent compounds. So you got the iron right, you got the oxide right, Grace, but not the tri. Okay. All right. But, we talked about these. We had 16 elements, metals that you knew that 100% of the time what their oxidation number is. All the other metals have a variable oxidation state. So we have to use the parentheses to designate. It's like the one we did earlier with the nickel 3, lead 2, we had a parenthesis. So what Roman numeral should I put here? What is the oxidation state of this particular iron? And sometimes remember the little hint I gave you guys about if you look at the subscript of the anion, that generally is the oxidation number of the cation. Okay. What is the subscript of the anion? What number is that? Oh. All right, well, let's move on. And this is iron 3. All right, iron 3. Because it's if you don't understand how that is, because the problem is this, you could be asked, show the decomposition of iron 3 oxide. And from that, be able to write the equation. Well, if you're given iron 3 oxide, you have to go and write the formula. Okay. And so that means iron 3 is Fe plus 3. The oxides are all -2. Okay. So we have this similar charges here. So we find a common number, which is 6. So we need 2 irons and we need 3 oxides. Okay. This then tells us that is the formula. All right. So the composition of iron 3 oxide, given us follows, so give you iron and oxygen. Whoa. All right. I was going to go through the process of balancing it and push the wrong button. We can do this a couple ways. Okay. But we can, I don't know why it's pushing there. Come on. Let's go back. All right. So if we have that single element by himself, so we leave him alone for right now. Okay. Let's focus on the oxygens here. We got a 3 and we got a 2. As we did before, we look for a common number. So if I put a 2 here and a 3 here, that takes care of my oxygens. Okay. Got 6 oxygens on both sides. Now, what that means is now I got 4 irons over here. No big deal. I put a 4 right there and I'm good to go. So everybody now is balanced. Okay. All right. So this is an example of a decomposition reaction. The takeaway again is this: you start off with a compound, you're going to do something to it, and you convert that compound back to the elements. Iron 3 oxide, also known as rust. It's a good way to get rid of rust. All right, here's an example of a combustion reaction. This is the combustion reaction of propane gas. And so you are given the hydrocarbon, right? So I can quickly write that down. C3H5, okay? This is called propane. That is a formula for propane, is shown here in two-dimensional model. The yellow dots represent the 3 carbons that are connected to each other. And then we got the hydrogens that are connected to their carbons. Okay, so that is the structure of propane. Now, what did I say about combustion reactions? What is the one reactant that I need? Without it, there's no combustion. Okay. What's that? Exactly, oxygen. And so we got to write oxygen. And furthermore, we know that oxygen is a gas. Okay. And we know that propane is a gas. Why do we know that? Because they tell us it's a gas. So it's a G for that. Oxygen's diatomic, right? And so I write that down. Now, what are the 2 products, the only 2 products that we are concerned about when there is the combustion of a hydrocarbon? What are the 2 products? There's only 2 products that you have to be concerned about. Any idea? CO2, you're correct, Grace. What was the other one? So CO2, and there's one more product, H2O, exactly. So those are the only 2 products that we need to be concerned about when it comes to the combustion of any hydrocarbon in here at Chem 130. Okay. So, and it's burning, so the water that you are creating really is in the gas phase 2 vapor. Okay, because you're burning this thing. Eventually you can condense that vapor and get water back in the liquid phase. All right, so now we have the equation, okay, but it's not balanced. So for balancing combustion reactions of hydrocarbons, the first thing we do is balance the carbons, okay? So here we have 3 carbons on the left. We simply need to put a 3 in front of carbon dioxide, and that balances the carbons, okay? So carbons are good to go. Step number 2, we balance the hydrogen. All right, the hydrocarbon here says we got 8 hydrogens, okay, as a reactant. We only got 2 in the form of water. So to get 8, we simply need to put a 4 in front of H2O. And that gives us 8 hydrogens. So hydrogens now are good to go. Finally, you balance the oxygens. Okay, so we got 2 oxygens on the left-hand side, but on the right side, don't forget, count all of the oxygens. We have some oxygens in the form of carbon dioxide and some oxygen in the form of water. So we got 6 oxygens coming as carbon dioxide, and then we got plus 4 coming as water. So we have a total of 10 oxygens on the product side. All right. 9 times out of 10, this number that you calculate is divisible by 2. So take that 10, divide by 2, gives you 5, and come back to the reactant side and put a 5 in front of O2. Why? Because O2 is diatomic. There's every molecule of oxygen has 2 oxygens. So I only need 5 molecules of oxygen to give me 10. And so here we are balanced, okay? Oxygens last. So we have a balanced chemical reaction. Let me clear my mess. And we write down the general equation, okay? And then we balance it by the steps that we take. Now, in this balancing, here's something to notice. For every molecule, for every 1 molecule of propane, think about this next time you're cooking out there, okay? I always think about it when I'm using my propane tank. Is for every molecule of propane, I need 5 molecules of oxygen. That's quite a bit of oxygen, okay? of oxygen to burn 1 molecule of propane. And then what that does, it produces 3 molecules of carbon dioxide, which, goes up in the atmosphere and then, kind of gets stuck up there and we got problems. Okay. And then we're adding more water to the system, adding 4 molecules of water. All right, but it's quite a bit of oxygen. Now, as we increase the number of carbons, it's going to take more oxygen. Now, sometimes, if you notice, we ended up with 10 oxygens here, a nice even a number divisible by 2, okay? There's examples that you don't end up with a nice number that's divisible by 2. You end up with a number that is odd. So how do we tackle that problem? Well, let me give you an example. Let's talk about the combustion of this particular hydrocarbon branch, which has six carbons and 14 hydrogens, okay? Actually, this has a general name of hexane. The prefix hex, 6 carbons. Ane, the A and E tells you it's a hydrocarbon. Like propane at 3 carbons, that's pro. Butane, we have butane lighter, that has a prefix for 4 carbons. Anyway, let's take this hexane and undergo combustion. So we need oxygen, okay? And the only 2 products we're going to be concerned about are carbon dioxide and water, okay? Which will all be in the gas phase. Okay, so step 1, we balance the carbons first, right? So we got 6 on the left, so we need 6 on the right. Step number 2, this is true for any of the hydrocarbons you're going to do a combustion reaction. We balance the hydrogens. So we got 14 on the left in the form of hexane, but only 2 on the right. So if we put a 7 in front of water, that takes care of our hydrogens. We're balanced. Finally, we balance the oxygens. Okay, so we only got 2 oxygens over here, but here we got 12 coming from carbon dioxide and 7 coming from water. So we have a total of 19 oxygens, okay, which is a little bit of an odd number, right? And I couldn't put 19, let me change the color here to demonstrate what I'm talking about. I can't put 19 here in front of O2 to balance it because that gives me 38, okay? So temporarily, I take, because I only need half of those oxygen molecules. So I can do a 19 halves temporarily, okay? All right, so I got 1 hexane plus 19 halves oxygen molecules, 6 of carbon dioxide, and 7 of water, right? Well, we don't leave any coefficients as fractions. So we need to get rid of that fraction. We need to get rid of that 2. All right, so I got 19 halves. Now, how can I get rid of that 2? What number do I multiply to get rid of that 2? To multiply, what number can I multiply here to 19 halves to get rid of that 2? Not a trick question. I thought I'd get rid of 2. What number do I need to multiply with? I want to say 2, and that is correct, okay? So if I multiply by 2, guess what? Those 2 cancel out, right? But like in mathematics, when I multiply one number, I got to do that to everybody, okay? So that means I take 2 and I multiply everybody by 2. So this is 2. All right, so it's 2 times 1, 2 times this, 2 times 6, and 2 times 7. All right, and so what that does let me get rid of this junk, is I get 2 hexanes plus 19 oxygens, okay, because the 2's cancel out, right? And 12 carbon dioxides and 14 waters. Okay, now let's do a double check. I have 12 carbons over here, right? And I have 12 carbons over here. That's good to go. 2 times 14. Don't I have 28 hydrogens on the left-hand side? Okay, on the right-hand side, I have 28 hydrogens. So hydrogens are good to go. Okay. For oxygens, I have 19 times 2, isn't that 38 oxygens? Right? Well, over here, I got 24 oxygens coming from carbon dioxide, and then I got 14 coming from water, so I got a total of 38 oxygens, and everybody is happy. Now, none of these numbers are divisible by 2. In other words, when you balance any equation, you want to bring it down to the lowest number, and you are at the lowest number, okay? And so this is what you do whenever you balance the oxygens and you end up with an odd number, okay? That being the case, you multiply everybody by 2 to get rid of that half. Okay, and then that balances out. You're good to go. So I need, for every 2 molecules of propane, hexane here, wow, I need 19 molecules of oxygen to burn that, which then gives me 12 molecules of carbon dioxide and 14 molecules of H2O. Okay. All right, so that's how we handle a combustion reactions, and this is basically the information that I just talked about: balancing, doing oxygen last. You know, your products are always carbon dioxide and water, and oxygen is always a reactant with your hydrocarbon. You balance carbons first, hydrogen second, oxygen's last. Okay. So you should be able to predict the reactants and products for the combustion of any hydrocarbon you're given, okay, and to balance them. And then if you end up with an odd number of oxygens at the end, then do what we just did. All right, so this brings us to the acid-base reaction, or a neutralization reaction, where, as you stated before, you have an acid proton reacting with the hydroxide, okay, to give us water and the salt. Now, here's the thing. 1 proton requires 1 hydroxide to give you 1 water, 1 molecule of water, all right? So if I have 1,000 protons, I need 1,000 hydroxides, which will give me 1,000 molecules of water, okay? And that's because it's a 1-to-1, okay? 1-to-1, it's called, we call that stoichiometry. So if I just need 1 of proton and 1 hydroxide, and gives me 1 water, then regardless, I can multiply that 1 with whatever number I need, right? It's analogous to some other things that we're going to talk about down the road when we get into stoichiometry, but just remember that 1 proton, 1 hydroxide gives me 1 water. So if I have 2 protons, I need 2 hydroxides. And I tell you this because this is how we're going to balance acid-base reactions, okay? We're going to follow the protons and we're going to follow the hydroxides. So we have the first one here is we have hydrochloric acid, HCl, reacting with barium hydroxide. All right, so when barium hydroxide goes in solution, it is creating two hydroxides. Okay. Well, hydrochloric acid only has one, but I need two protons. Right? So I need to put a 2 in front of HCl. That tells me that I need 2 molecules of hydrochloric acid to produce 2 protons, because barium hydroxide is producing 2 hydroxides, and I need to neutralize that hydroxide. So that being the case, how many waters am I going to make? If I have 2 protons and 2 hydroxides, how many waters am I making? You can tell me that. 2 protons, 2 hydroxides. How many waters am I going to make altogether? Okay, well, let me give you an analogy. Okay, something totally not related to this. All right, let's say I got a tire, specifically a bicycle tire. It's my artwork of a tire. And I have a frame, bicycle frame for a unicycle. Okay. And when I put those together, I assemble them, I got my assembled unicycle, right? Doesn't it take one tire for every unicycle frame to give me one assembled unicycle? If I have 200 tires, how many frames do I need? How many unicycle frames do I need if I have 200? Good, exactly. That's good. Okay, I will need 200 frames. How many assembled unicycles would I make? Assembled unicycles. And again, 200. Okay, which is no different than if I replace that bicycle, that tire with a proton, and if I replace that frame with a hydroxide, and I assemble those two to give me the assembled water molecule, isn't that the same scenario? If I have 200 protons, I'm going to need 200 hydroxides, which will give me 200 water molecules. All right. With that being said, if I have 2 protons and 2 hydroxides, how many waters am I going to make? Exactly 2. Right. Now we're getting somewhere. And there, in that example, I used a unicycle, but my other analogy would be a bicycle, because a bicycle will be a ratio of 2 to 1, two tires to 1 frame, right? And then if I had a tricycle, it's a 1 to 3 ratio. And if I had a quad, I have 4 tires, a car, 4 tires to the car. That relationship is something that we need to start understanding, because that's important when we start doing the calculations here. All right, and so we're going to create 2 molecules of water. All right, now I'm going to have to put together the salt, because remember, the salt comes from the metal and the non-metal. But before I put them together, I need to put them in ionic form like we did before. And we know that barium has a +2 charge. How do we know that? Barium is a group 2A element, 2 valence electrons. It's a metal. It's going to lose those 2 valence electrons, have a +2. But if you forgot that, hydroxides have a -1 as per the polyatomic ion table. There's 2 of them, hydroxides. So that infers that the barium has to be a +2. Now the chlorides, like any halide, has a -1 as an ion. So that means I need 2 chlorides for every barium. So our formula is BaCl2. Okay. And so let me erase some of this mess here. All right, so now let's take a look and see if we're balanced. Okay, I have 2 hydrogens coming from hydrochloric acid, and I got 2 coming from hydroxide. So there's a total of 4 hydrogens on the reactant side. And there are 4 hydrogens in the product side, all in the form of water. The chlorides, we got 2 chlorides on the left side, and guess what? We got 2 on the right side. So they're good. We got 1 barium on the left, 1 barium on the right. Everybody's happy, we're balanced. Okay, and we did that how? By following the protons and the hydroxides. The corresponding salt balances itself by default. Okay, clear up my mess here. All right, 2 waters. Okay. All right, let's take a look at the next one. This is phosphoric acid. Remember, it's one of the weak acids we talked about. Question is, how do I know that's an acid? As I stated, 9 times out of 10, hydrogen is written first. That's a good suspicion that that is an acid. You can go back and check and also verify. Yes, H3PO4 is an acid. Okay, how do we know the calcium hydroxide is a base? Because in parentheses, you have the hydroxide ion. Okay, so the hydroxide will produce, the calcium hydroxide will produce 2 hydroxides, right? Phosphoric acid will produce 3 protons, all right? Do we not have a dissimilar number here? We got 2 and a 3 ratio again, right? What have we been doing in the past? We've been looking for a common number, which means that the common number is 6, right? So in order to get 6 hydroxides, we need to have 3 calcium hydroxides, right? Because that gives us 3 times 2 is 6. So that gives us 6 hydroxides, and I'm writing them out individually so you can see that, okay? Which means that I need to have 2 phosphoric acids, which will give me 6 protons. So now I got 6 protons, 6 hydroxides. I know I'm going to make water, but can you tell me how many waters I'm going to make with 6 protons and 6 hydroxides? There you go, you're getting it? Exactly. So I'm going to make 6 waters. Now, water is one of the products, is a liquid. Water, let me tell you, I've seen some pictures, especially in the beaker drawings, where water is shown breaking up as ions. It doesn't happen. Water is a covalent compound and does not dissociate into the protons or hydroxides, okay? All right, so water remains intact, and it just, when you make it at room temperature, it's a liquid. That's it. So its physical state is L for liquid. All right, so that balances. We're following the protons and the hydroxide. Okay, and I wrote them out like this so you can see what's going on. I'm going to make 6 waters. So I think we're going to be good as far as balancing the oxygens and the hydrogens. Now we're going to worry about the salt, which is the calcium, and the nonmetal, which is the polyatomic ion phosphate. So before we do anything, we're going to put them together in ionic form. So calcium has a +2, as in the case of barium. Okay. And the phosphate has a -3. Check your polyatomic ion table. That's where the phosphate ion came, by reacting phosphoric acid with a base to generate the phosphate ion, actually the 3 protons. All right, so again, we have a dissimilar situation here, which means that we're going to need 3 calciums and 2 phosphates. So our formula is Ca3 parentheses PO4 subscript 3. Okay. Now we can go and check to see if everything's balanced. We got 3 calciums. Change the color a little bit. We got 3 calciums on the right. Guess what? There's 3 on the left. We got, where are we at? Oh, what did I do? Nobody caught that. That's not a 3 there. That's a 2. And like, no, that's not right. It's a 2 because we need 2 phosphates, not 3. And so we got 2 phosphates on the right. And guess what? On the left, we got 2. There's a number 2 in front of phosphoric acid. So we got 2 phosphates. So those guys are happy. And if you check your hydrogens and so forth, those are all going to fall into place because we balanced the protons and the hydroxides. So everybody is balanced. And let me clear my mess and bring that together. Okay. And so the big takeaway here with respect to acid-base reactions is this. 1, recognize that you're dealing with an acid, and recognize that you're dealing with the base. Also recognize that when you have a proton and the hydroxide, you're only going to get water. And then what's left is the salt, which is the result of the metal of the base and the non-metal of the acid. Okay. To balance them, follow the protons created in the hydroxides, because 1 proton, 1 hydroxide creates 1 water. So if you follow that, you balance your water out first, and then write the salt in ions first, in ionic form first, before you put them together, to make sure you put them together in the right ratio. And the salts will just fall into place and balance themselves out by default. Okay. So there's a good example of an acid-base reaction and what you can do to help balance it out. All right, now this brings us to the single replacement reaction. That's the one I explained, where you have the element of M, okay, a metal of some sort, reacting with an ionic compound, okay? And if this reaction proceeds, the metal, the more reactive metal, will replace the metal that's in ionic form to create a new ionic compound. Then it would take that metal that was in ionic form and convert it back into elemental form, okay? And the driving force is this, is that the most reactive metal is going to want to be in ionic form. And we determine the most ionic metal by using the activity series, okay? So we need to know that, and this is what the activity series is. It's on the periodic table, and it summarizes this. So you can see here that we have one set here, that it's highlighted. You'll find it on the product table as being in bulk. These metals here, these 6 metals, starting with lithium, the way it reads is across the board is this. Lithium is more reactive than potassium, they're more reactive than barium, more reactive than strontium, et cetera, until you get to the least reactive metal, which is way over here on the right-hand side, which is gold. Gold is the least reactive metal. It's called the noble metal because it takes some very vigorous conditions to get that metal to react. Now, here's the sometimes the confusing part for students is you see this in here, it says H in parentheses. What that represents is this whole scale is a relative scale, okay? And it's relative to hydrogen gas or the proton, okay, or water. So the scale is all relative to, and this will make a little more sense in a bit. All right, so that's how the scale runs. Now, the ones written in white are the most reactive metal. They react with water like that. They're dangerous chemicals, dangerous metals, very reactive. And the thing is that those in white will react, and I'm going to designate these metals in white with the letter M prime to show that it's just lithium through sodium. If they are in water, they react violently, and in the presence of water, they react with water to produce hydrogen gas plus the corresponding metal hydroxide. So if we were to take some sodium and put it in some water, it would be very violent. In fact, you would hear an explosion, a little pop, because it gives off so much heat that it will ignite the hydrogen that's being generated. And then we can check the pH of the solution after everything's done. And we would take red litmus paper. Remember that litmus paper test, and convert it to blue because it produced a hydroxide. And that's what happens when those species react with water, okay? Now, the other species, which starting with magnesium and going all the way to lead, now they're not as reactive as the ones in white. They take a little bit more, they require a little bit more acidity to get them to react. And so what happens is to get those to react, I'm going to designate those as M double prime, and that represents the metals from magnesium to lead. And they require like an acid source. And I'm just say H and just call it X. It'll be any acid. And when they react, they also, with acid, they also produce hydrogen gas, okay? Plus the metal X combination, the ionic compound. Nothing to do with base. X could be chloride, bromide, phosphate, whatever, but it will generate, you'll see a lot of bubbling going on when they're in acid, okay? So they require a little more vigorous conditions to get those to react, okay? Which leads us to these other ones here, copper to gold, very unreactive. They require some vigorous acid conditions to get them to react. So for our purposes, we're just going to call them, just call it as they don't react, okay? Can they react? Yes, but extremely vigorous and harsh conditions to get them to react. Okay. Now, excuse me, the way this activity series works, it says here that the most reactive metal wants to be in cation, it wants to be in a compound ionic form. So lithium would rather be lithium plus than be lithium if it has the choice, okay? especially if the metal that it's placed with is a metal that less reactive than lithium. It will change places. Okay, this is how that's working. Okay, the least reactive metal wants to stay as an element. So if it's an ionic form, it's going to drive itself to become an element. Okay, all right, so don't forget the other reactions that I just designated for the ones in white were reaction of water to form hydrogen gas and the metal hydroxide, and then the metals between magnesium and lead to give you hydrogen gas plus the metal X. Okay, takes a little vigorous condition, more vigorous conditions. All right, so with that in mind, if the most reactive metal is already in ionic form or in the compound, then there's no reaction, okay? It is only when it's not an ionic compound, the most reactive metal, that then you get a reaction and you essentially just switch partners. And of course, for 4, we're gonna write the stage, their physical states. All right, and then of course, at the end, we balance it. And balancing these type of reactions are like analogous to the other ones that we did by trial and error. All right, let's take a look at this. So we have here zinc nitrate plus sodium, and then the question mark. The question is, will this reaction occur? All right, so what we do first is we just identify the metals, and we don't care if the metals are elemental or in zinc. We just identify and we compare them metal for metal. So we identify here's zinc right here, and here is sodium right there. So what this says is that number 1, that sodium is more reactive than zinc. Okay. Second step is to ask, is sodium, which is the most reactive metal, is sodium in ionic state? So is sodium an ion? Here, the answer is no. If the answer is no, then you have reaction, positive reaction. If the answer is yes, you get NR, no reaction. Okay, so the answer here is no. So there is a reaction, and you essentially exchange position of the metals. Okay, sodium. All right, so zinc is now going to go from ionic form, and it's going to go to elemental form. Okay, and then the sodium and the nitrate are going to combine, and like we've been doing before, write them in ionic form first. And so we write sodium plus, and then the nitrates are NO3 minus. Okay, so we put those together and a 1-to-1 ratio. And now we have written the equation, and the next step is to balance it. In this scenario, since you have polyatomic ions, follow them. Okay, so we got 2 nitrates on the left side. If we put a 2 in front of sodium nitrate, that balances out the nitrates, but it kicks up the sodium, no problem. Go to the sodium metal. Oh, I see what I'm trying. You got too many arrows here. Nobody picked up on that. Here we go. It's supposed to be a plus there. We put a 2 in front of sodium. That balances out the sodium. Zincs are good. 1 zinc on both sides. 2 sodiums on the left, 2 on the right, 2 nitrates on the left, 2 on the right. We're good to go. Okay. And so that's the reaction, because again, the driving force is sodium wants to be in more into ionic form than zinc under these conditions. Okay, we're just comparing sodium and zinc. What it also means is the opposite. If the reaction, the opposite reaction was given, say you got sodium nitrate plus zinc, okay, and then you're asked, is this reaction going to occur? Well, you go through the same questions. You go through the activity series, you see that sodium is the most reactive metal, that doesn't change. And then you ask the question, is the most reactive metal in ionic stage? Here, it's yes. It is in ionic form. It's in the form of sodium nitrate to begin with. So in this scenario, you get no reaction, okay? And so the point being is this, if you get a reaction in the forward direction, in the opposite direction is a no reaction. And this is true for a forward reaction that says no, it's not no reaction. That means that the opposite direction is positive, okay? All right, let me clear this up and don't forget our states, sodium nitrate, definitely sodium nitrate, the fact you got sodium, the fact you got nitrate combination, that's a aqueous solution, all soluble, all right? All nitrates, if you recall, are all soluble, regardless of what the cation is. And then sodium, both sodium metal and zinc metal are both solids. Of course, we're not going to write 2 nitrates for the sodium because that infers that sodium has a +2 charge, and that's not the case because we know sodium is a group 1 element. Okay. All right, let's do. We've got a few minutes here. We're going to end at 4:15 because we did have a late start. All right, so here's the similar scenario. This time you are. Let me change the color here. Comparing aluminum with strontium. Okay, so first step is find them on the activity series. Excuse me. There's SR and then aluminum. Okay, and so that tells us that SR is more reactive than aluminum. Okay, and so next question is SR ionic? Okay, because that's the most reactive metal. And in this scenario, it's yes, it is ionic already. So the result is no reaction. Okay, no reaction because the most reactive metal is already in ionic form, which means that if you're given the opposite direction, that meaning if you start out with this, let's say aluminum bromide plus strontium, and you're asked the same question, and you follow the same question 1 and 2, and this time instead of yes is going to be no, which tells you yes, there's going to be an exchange here, and you're going to get aluminum plus strontium bromide. Okay, I'm not balancing it, but yes, in the opposite direction, you will get a reaction. Okay. Well, in the opposite form, this is what I mean by opposite form. Aluminum versus being elemental form versus ionic form, and vice versa. So no for the top reaction, yes for the bottom one. Again, because the most reactive metal wants to be in ionic form. Okay, now here's a little bit different here, okay, because we're not dealing with here we got 2 metals, one's in the elemental form, one's in ionic form. What we're dealing with is hydrogen. Hydrogen is our reference point. And so the elemental form of hydrogen We go to the product, to the activity series. Where do you go? Right here. This is the element to form of hydrogen, obviously, is H2. And the ionic form of hydrogen is H, and it could be water, depending on which metal you're working with, okay? So this is the element to form H2, ionic form is H+. So here, the question is, we're comparing hydrogen versus aluminum. So we go back through the activity series and find out who is more reactive. Here is aluminum right here. There's hydrogen. So what this means is this aluminum is more reactive than hydrogen. Okay. Plus the fact, if you recall, when we had magnesium all the way up to lead, anytime you had an acid react with any of those metals, you're going to get a positive reaction because those metals are all before hydrogen, and therefore they are more reactive than hydrogen, and therefore the following would occur. And this is just using the activities. So question is the most reactive metal or most reactive species in elemental form? The answer is no. Aluminum is more reactive, and therefore there's a positive reaction. So this hydrogen gets converted from the ionic form to the elemental form. Then we're going to exchange the aluminum with the hydrogen. But we first put them in ionic state first. So aluminum is a +3, and the chlorides are -1. Okay, aluminum is a group 3A element metal. It will have a +3. Chlorides are group 7A. Okay, so the formula for aluminum chloride is aluminum Cl3. Okay. Let me clear my mess and we'll stop it here. And so you have the reaction. Hydrogen is a gas. Aluminum chloride is aqueous because solubility rules dictate it to be an aqueous solution because it's soluble. And then we balance it up. Okay. So I'll leave you with that. You can work through that balance and see if you can figure it out how they come up with 2, 6, 2, and 3. And let's see, back up and we'll leave it on 38. Okay.